Okay, so in this section, what we're going to be doing is talking about something called collision theory. And I introduced that a long time ago, like in the beginning. I know your book doesn't really talk about it much towards the end, but so you may have to go back and review, like it's actually in the first video segment for this chapter. Okay. So in collision theory, we talked about a couple of different things. One is molecules have to collide, right? They have to have enough energy when they collide, right, to go above. And we talked about the activation energy barrier, and we'll talk about that a lot in this section. It's really what this is about. And then, but they also have to have the proper orientation when they collide. So there has to be a collision, right? It has to have enough energy, and it has to have the proper orientation. If any one of those three things doesn't happen, then the reaction doesn't happen. So lots of times molecules collide together, they don't have enough energy. So how do we know, like, what do we talk about when we talk about energy? So we have to go back to kinetic molecular theory, and that's from the gas law chapter. And we know, right, that kinetic energy increases as temperature increases. So this is just a little video segment that shows the relationship between energy of molecules and temperature. So as it runs, we'll talk about it. Okay? So first of all, what is this graph, right? This is the number of molecules. This is the meters per second. So that's how fast they're moving. And remember, kinetic energy is equal to 1/2 mv squared. So the kinetic energy goes with the square of the velocity. So what's going to happen in this video is we're going to change the temperature, and this graph will move according to as we increase the temperature. Now, this red graph, this part of the graph that's here, right, is showing the distribution of velocities for the molecule. So let me turn this on, see what happens. So now the temperature is increasing, and what you'll notice is as temperature increases, it's not like all of a sudden, right, there's enough molecules to go above that velocity. They said 1,000 meters per second. But eventually, as it turns out, right, when you get the temperature high enough, almost all the molecules will meet the criteria of having a high velocity in this particular instance. What does that mean? Remember, let's say that velocity is the activation energy. As you increase the temperature, it doesn't suddenly become all the molecules react. It's a portion of the molecules. And in collision theory, right, this is treated as an exponential function, and we'll get to that in a little bit. But still, as temperature goes up, kinetic energy goes up, okay? Here's some other videos to watch.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
So what we're doing right now is we're looking at a reaction. I'm going to write the reaction out. You saw these are the reactants. So the reaction is ozone plus NO, right? So let me write this out. Ozone, O3, plus NO. And that's going to make a product. But these molecules collided together, didn't have enough energy to produce the product, right? So let's look at the next one.
For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies,
slower,
a reaction does not occur, and the molecules separate without reacting.
So again, situation is not enough energy, right? First one was not enough orientation, not enough energy. We could increase the temperature and that would work, right? So we still don't know what the products are. So let's watch the next one.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
And you notice what happened there. Let's see if I can scroll back slowly, right? They come together with the correct orientation and sufficient energy. And this is the point where the reaction, the energetics of the molecules matters. You have to break a bond and make a bond. That's happening right there. Okay, that's the point at which you need all that energy to go into the molecule to make the products of the reaction. This particular instance that's right here is known as the transition state. It's the highest energy point between the reactants and products. Like I said, it's when all that energy is needed to break and make bonds. Okay, so we know what the products are now. It's NO2 and O2. And sort of what you just saw right there is known as a mechanism for the reaction. That's really like the next section. But we're trying to understand kinetics so we can understand what's going on in the reaction, how it actually takes place. Okay, so in collision theory, we think of the rate constant as being composed of three parts, okay? One is the collision frequency, because they have to collide, right? The second one is that they have to be correctly oriented. Right? And the third one is the molecule. There's a certain number of molecules that have enough energy to react, and that part's probably the most complicated. Okay, because really what happens is we take the collision frequency and we take the orientation, and we combine those terms into what's called a pre-exponential factor, and I'll show you what that means in a second. It sounds complicated. It's really not that complicated. So this then becomes boiled down into A times F. So we got to figure out what the fraction is in order to do this analysis. Okay, so fortunately somebody did all the hard math, and this is the result. So the fraction of molecules with enough energy is given this term. So the equation becomes this: K is equal to A times e to the minus EA over RT. Now, EA is the energy, the activation energy, usually in joules, but it could be kilojoules, but it's usually in joules. Okay. And A is that combination of Z and P. Okay. So it's the ones that collide that have the right orientation. That's what that means. Now, this is what we call a pre-exponential factor. Because it comes before the exponential. Okay, anyways. Yeah, it sounds really complicated, but I don't know why they didn't just give it a simple name. But anyways, they didn't. So, I guess the things to next know are, right? Remember, that's the gas law constant, but it's in different units. It's this value here. So this is R. You may remember it if you probably used it somewhere in Chem 1A, but that was a long time ago. So anyways, it's the value of R that's in units of energy, joules, okay? And the temperature, so that's what that is. The temperature just has to be in Kelvin. And like I always tell students, when you're using R, just look to see what the units are in R, because that's what you need to use in your calculations. Okay. So just to give you an idea of what's important and what's not, right? For a 10-degree change, so 273 to 283 Kelvin, with an activation energy of 100 kilojoules per mole. Now, I'm telling you, that's actually a really large activation energy. Typically, they're in the 30 or 40s, but I just wanted round numbers. Okay, you get almost a 500% increase in the magnitude of the rate constant. Okay, so the reaction goes 5 times faster. 500% goes 5 times faster for a 10-degree temperature change. Now, there's an experiment that we're going to do on video, right? And you'll see this as I change the temperature by, this is again Kelvin degrees, 10 degrees Kelvin. The reaction is so fast, it's basically you can't measure the reaction rate. It just is that fast. Okay, so having said that, right, if you change the temperature 10 degrees Celsius, it turns out the collision frequency only changes about 2%. So in terms of like what's important and what's not, people tend to ignore changes in the pre-exponential factor, because the frequency doesn't change that much. Collision frequency doesn't change that much. And the orientation factor doesn't usually depend that much on temperature for what we're doing. But for certain, in like biochemistry, temperature makes a big difference, right? But in our situations, it won't make that big of a difference. Now, yeah, so that is the Arrhenius. This is called now, this K is equal to A times e to the minus EA over RT, is known as the Arrhenius equation. You'll have seen it in Arrhenius is also responsible for a lot of the stuff you learned early on about acid-base theory. He's a Swedish scientist. I always like him because his name, because he was Savante Arrhenius, I believe was his name. So it stands for genius Arrhenius, right? Savant, smart Arrhenius. Anyways, so yeah, this becomes what's known as the Arrhenius equation. So let's look at an energy diagram. We've discussed this in the worksheet, and we've also sort of been discussing it. We've discussed them a little bit in Chem 1A, but the activation energy is the energy you need to overcome for the reaction to take place. When you think about the activation energy, though, right, we have to think about an energy diagram that it superimposes on top of. So like in Chem 1A, and you probably learned like a version that looked like this, or it was the version that is in your book that just goes straight up. There is no time factor in it. But in an energy diagram in Chem 1B and throughout the rest of your chemistry career, however long that happens to be, on the x-axis is the time. It says progress of the reaction. I'm just going to call it time. But it's not time in the sense like a stopwatch time. It can be related to that often, but it's typically just from the beginning of a reaction to an end of a reaction or to a product. So we oftentimes in Gen Chem will show two lines and the line that goes between them. Now, in the forward direction, though, there's going to be a barrier because you got to get to that. Remember, we call about the transition state, right? You had to get to the transition state. This is the activation energy from the bottom to the top. So that's what I've shown over here. So the forward activation energy is slow or is large for this one, which means the forward reaction is very slow. If you think about it, right? Large activation energy means very few molecules can get over the activation energy. So that means very few molecules per second will actually react. On the other hand, the activation energy for what we call a reversible reaction, where you can go forwards and backwards, right, is really small going in the backwards direction. So this activation energy being small, right, relative to this activation energy being large, means that the reverse reaction is much faster than the forward reaction. Now, just to bring this up, that means there won't ever be a lot of product in this reaction. It will be formed, right? But as soon as it forms, it activates, goes back into the reactants. And we'll learn about this concept when we talk about equilibrium in the next chapter. How much should you expect when you just allow the reaction to run of reactants and products, okay? So yeah, the activation energy is small. Now mathematically, you'll see that 2 kilojoules, right? This is delta H. This is the enthalpy between the reactants and products, right? Plus the 83 is always going to be equal to the activation energy in the forward direction, okay? So you can see mathematically there's a relationship. Now, what if it had been like this instead, right? Then to get the activation energy for the reverse process, right, that would have been all the way up here. That would have been this plus this. So graphically, you can do this analysis. Sorry, that was supposed to go to that point there. Let me just fix that. Right. You can relate activation energy is if you think about whether or not it's going down in energy to the products or up in energy, you could think about the relationship between the activation energy of the forward and the reverse reaction. Now, if you wanted to know this, right, all you have, and you had the activation energies, you could figure it out because this value here, right, is just the large activation energy subtracting off the small activation energy, right? Just a couple of other things. It's a couple of things where people kind of get confused. Um, the activation energy is not dependent on temperature. Okay, so when you change temperature and a reaction goes faster, it's simply because molecules have more energy, okay? Or less energy if you cool it down, right? So that it'll go slower. Now, if the activation energy is large, okay, here, that means this is large. That means the effect of changing temperature will also be large. And if the activation energy is small, then typically the effect of changing the temperature is small. And if you're looking at forward reactions versus reverse reactions, right, depending on which one's larger, one will be more affected by temperature than the other. Okay, yeah, that's good. Another term, and I actually skipped a slide that you want to look at. It just kind of summarizes what I just said. But another thing to think about is we talked about the transition state, right? The molecule that is formed, right, or the species, I should say, because it's not really a molecule that is formed at the top of the activation energy barrier is known as the activated complex. Okay, so I don't remember if this has sound or not. Let's play this and see what it comes out
The bimolecular SN2 mechanism for a nucleophilic substitution reaction, the formation of the bond between the carbon atom and the entering species occurs simultaneously with dissociation of the bond between the carbon and leaving group.
All right, so let's go back. So we don't have to listen to the sound now. We'll go forwards and backwards, right? So, and you don't need to know SN2 and SN1. There's another one coming later. Fluoride comes in. It hits with enough energy. It actually causes all the hydrogens to move away. Or maybe not. I broke the video. Look at that. Let me do this again. All right, I think I got it now. So we're going to move forward in the video. All right. Nope, I really did. Oh, there it is. I'm going too fast for my computer, so I think what I'm doing.
Carbon and
It's actually back here.
Species.
There we go. Right about here, the fluorine comes in. Yeah, there we go. It breaks the bond between the chlorine and the carbon, right? But it does so by coming through the backside. So it comes in, and really the way it's going to break that bond is by stealing the electrons or the orbital that's bonded to the chlorine. It steals that, and at the same time, the hydrogens have to move out of the way for this to happen. This is probably around the highest energy point in the reaction. Now, if you remember Vesper theory, going back to Lewis structures and then shapes of molecules, right? Remember we talked about we want the maximum distance between atoms to get the lowest possible energy. And that's why we get like tetrahedral shapes. And in this case, this is known as a trigonal bipyramid. So the transition state, right, is this, or activated complex, that's the species that we're looking at here on the screen, right, is got 5 atoms, right, in a small space as a trigonal bipyramid. And the result is there's a lot of energy, what we call steric, but it's like space strain in the molecules as they push against each other in their electron clouds. Okay, so that's the idea of the activated complex. It's somewhere between the reactants and the products, right? And it's got a lot of stuff going on, but it's got atoms close to each other. You got bonds breaking and bonds forming in this case. Okay. The reaction, the overall reaction, summarized like right down here. Right. So I have CH3Cl3 at the beginning. Fluoride, right, makes the CHF3 and chloride. And this is actually known as, this is what chloroform looks like. And this is known as fluoroform because it's made out of fluorine instead of chlorine. Okay, so how do we determine the activation energy from a set of data? And it turns out you have to take the log of both sides. So we're going to basically do what we did in a first order reaction is we'll use logs to simplify our equation. Now, it doesn't sound like it's going to be simple, but I'll show you the math and you can review it, right? So I'm going to take the log of both sides. So I'll have ln of k. That's going to be equal to the ln of, and then everything that's there, right? A times e to the minus ea over rt. I'll write it like that. Now, remember, when you have the log of a number, you can say that the log of, for example, log log or ln of a times b is just equal to the log of a plus the log of b. And you'll see how this simplifies for us because this becomes, right, ln of k is equal to ln of a plus ln of e to the minus ea over rt, like that. So what does the right term do? It's the anti-log function, right, and the log function, and so they cancel each other out essentially. So now I can write that the ln of k is equal to the ln of a. Remember, that's the pre-exponential term too. It's not concentration. Plus, right, and then actually let me just do minus. I like saying plus, but it's confusing. ea over rt, like that. And so that is actually a relatively easy thing to analyze. Well, compared to like, we've already done like the hard thing of learning how to do it for first order reactions and second order reactions. What you'll do is you'll graph this as y, and then for your x-axis, right, you're going to graph 1 over t. So what does that mean when you do that, right? Now, I'm going to substitute it for you so you can see it, right? This would give me ln of a, right, minus ea over r times x, but x is 1 over t, right? So that means, right, this is your y value, that's your x value, this is your slope again. So again, just like we did in first order and second order and zero order reactions, we're going to use the slope to figure out what something is. In this case, the activation energy divided by R. Okay, so here's the series of data, right? I need a bunch of rate constants. So it actually takes a lot of experiments to get this information, right? You've already seen, this is what we spent a lot of time doing, is figuring out how to get a rate constant. So each one of those represents a series of experiments, and they all have to be done at different temperatures. So I have a series of temperatures here. Now this is degrees Celsius, right? And this is rate constant, and I'll graph it. So what I did is I took the temperature and converted it over to Kelvin, and I took 1 over temperature. That gives you my x values. My y values are just the logs of the rate constants from this table, these values right here. Now, once I have those, right, I graph them, and so this is a graph of that data. And again, it kind of looks weird. It takes a bit to do it. And then the slope in this case is this. So EA over R, sorry, I should say minus EA over R, actually, that's missing there. That's my slope, is equal to minus 19050. And let's just stick with many sig figs do I have here? 3 significant figures over here. So we'll do that. And then the units are just 1 over Kelvin, like that. So that's your slope. The units are 1 over Kelvin, because to calculate the slope, you'll do like log of k minus log of k, and all the units cancel out. I showed you that earlier. And this is just 1 over temperature on your x value. Oh, I'm sorry, this comes up to be Kelvin. So rise over run is just going to give us Kelvin as the units, because I'll have no units at the top and I'll have 1 over Kelvin at the bottom. But I used linear regression to do it, and we'll talk about other ways to do this as well. So in order to get the activation energy, then I'm going to have to take EA, right? It's going to be equal to R times 19050 Kelvin, like this. The minus sign drops out because I canceled the minus negative sign on both sides. And so now I just have to plug in the value for R, and this is 8.314 joules per mole times Kelvin. So that'll give me, and I'll pull up a calculator real quick. Okay, I'll try to pull up a calculator real quick, but apparently, there it is. So 19050 times 8.314, and the units, the Kelvin will cancel, right? And that's 158,381 joules per mole. I think it was 381. Now, typically these values, it looks like a huge number, right? Typically these values are done in kilojoules, so that ends up being 158, 3 significant figures in this case, kilojoules per mole, like that. So anyways, once you get the slope, then the actual rest of it's not too bad. You just multiply by R and then convert it to kilojoules usually. And this is actually a fairly large activation. And, you know, it's funny, I forgot I actually had it all worked out on the next slide, but that's the values worked out, so you can see how I got the same answers. So let's say you wanted to find the rate constant at a different temperature, right? How would you do that? Well, in order to do that, you know that your equation looks like this. Now, why do you know, oops, sorry, not like that, like this. Why do you know your equation looks like that? Because in the graph, right, I know ln of k is equal to ln of A minus EA over R times 1 over T. That's just the Arrhenius equation. When I did my linear regression, oh, sorry, I meant to go backward to slide, not here. Oh yeah, here it is. It actually gave me this value. So I just plugged in my minus EA over R, my slope. That's this value here. I plugged in the temperature that I was interested in knowing the rate constant at, and then that gave me the natural log of my rate constant. So this gives me ln k. This is ln k still, right? It's all the way over here, so I just rewrote it. And then what you do is you take the anti-log, so you take the exponent of that number, and that gives you your rate constant at that temperature. Now, that's the way we do it normally. You don't have to do it that way. There are other equations, and that's what I'm going to show you next. And this is typically the way book problems are solved. But if they give you a set of data and you want to do it on your computer, you kind of saw how I did it earlier in the lecture. Okay. So this is now going to be how you do this with an equation. Now, I always like to show students where the equations come from.